Okay, all right. So next, now let's understand the conversion of the R-type instruction in the machine to its machine code. Right, that's the assembler first job. We write a assembly code and how it translates into a machine code. So machine code, there is the format, like each R type, I type, and J type has predefined format specified, which tells that it's a 32-bit for these 32-bit MIPS, and first 6-bit is of function type. Second, these 5-bit is of shift amount. I'll come to that later. What is that? And then we support like the 5-bit for RD, register D, and then 5-bit for register T, 5-bit for register S, and 6-bit at the higher side, MSB side, for the opcode. Okay, now what is this RT/RD, right? This is the, for example, this is the assembly code looks like your mnemonic followed by RD, RS, RT. So in this example, your RD is R3, RS is R2, RT is R1. Okay, so there the RS, RD, and RT. So that's the assembly code format, how you write that corresponding assembly code. Now this example, I have that same example here. So here at this point, you need to know what is my opcode, and for R type, what is also my function code. Okay, so for all the R type instruction, your opcode is 0. So that's why in earlier slide you have seen that if the first 6-bit is all 0, they can imply to different instruction. But what is certain that if that first 6-bit is 0, it is of R type instruction. It is of R type instruction. And each of these instruction, different R type instruction, are differentiated from each other with a function code. Okay, so this function code is going to be different. So for add, its function code is hex 20. And this is my RD, this is my RS, and this is my RT. So what shall we do? This is my mnemonic, and RD, RS, RT. So add this instruction will be mapped with 6-bit of opcode, which is all 0, and 6-bit of function code, which is hex 20, which is 100000. Then comes the R3, which is RD, and RD's bit positions are 11 to 15. Okay, these 5-bit. So this is one point you need to be very careful, right? This does not follow the sequence of the format. RD comes last, RS comes first after the opcode, and then RT, then RD. So we place the R3 and we take that index of that R3 for in this example, right? 3, we pick up that and translate into binary, which is 5-bit binary 00011. And then R2, similarly, we place the binary 5-bit binary for 2, and then R1, RT places we put it as a binary code for 1. And now how about this guy, shift amount? Shift amount, if something is unknown in the hardware world, the safest value you can put there is all 0. So if you don't know a field value which is not relevant for one instruction, you just put 0 there. Okay. So what is this field for? This is for basically your shift left logical and shift right logical, SLL and SRL, these two instructions. Okay, and there you can specify something like SLL, R3, R2, and 15. It looks like a I-type instruction, but that is not a I-type instruction. So in that case, you need to place that shift amount, which is encoded directly with these encoded directly within this instruction, you need to put that shift amount into this field. Okay, and in that case, I believe you need to consult with that first page of the textbook, which has a green page which tells about all the code conversion and details about the register convention and stuff like that. You need to consult that, but I believe this R2 in that case will become RT. Okay, and RS you put 0 there. RS you put 0 there. So it becomes RT, but we need to check. But point is that in that case, the other field become unknown to you and you put 0 there. Okay. Anyway, so this is how you place the bits in the corresponding field of the format, and your machine code become that. So this is exactly what an assembler does. It looks and parses and break up these one assembly statement and look at the mnemonic, determine it has a lookup table to, okay, for this mnemonic, this is my opcode, this is my function code, this is of art type, then for art type I need to place this value, this value, this value, corresponding bit pattern into corresponding fields, fill up that, and that becomes your machine code. And of course, you can compactly represent this machine code into a hex. You just divided them into a group of 4 and you just write that corresponding hex digit. So next, we'll see the converting an I-type instruction. So I-type instructions format is like this. Your opcode, which is like first most significant side 6-bit, and then RS, RT, there is no RD, and but the 16-bit is immediate. So 5-bit, 5-bit, and immediate 16-bit. So assembly code mnemonic, something like assembly code format is mnemonic, RT, RS, and immediate. All right. So for example, if I have an add I R1 R1A, opcode of the add I is 08 hex, where add I is a mnemonic, this is my RT, R1 is also my RS, and then immediate value, then we can put the 08, that hex code, into corresponding 6-bit opcode, and then the immediate value into corresponding 16-bit representation, and 1 to 5-bit 1, and 1 to another 5-bit 1. So we place these, and then we have the machine code for 32-bit machine code, which we can compact it in a hex format. That's a different representation, right? It's just binary versus a hex representation. So this is your machine code for the I-type instruction, and this is how you generate the machine code, or assembler generates the machine code for a given I-type instruction. In similar notion, J-type instruction has this format. Before we go to J-type instruction, just one point to note: if there is a hex defined, so you just convert it blindly to whatever value you can derive out of it, prepending zeros if needed. But if it is a decimal representation, some assembler actually takes also decimal representation. The assembler you will be using in this class also will take the decimal representation, also binary representation, I think. So let's say if someone writes a minus 15, for example, here, add I, RI, R1, R1, and minus 15. What you need to make sure that you represent that minus value or negative value in a 2's complement, 16-bit 2's complement format. Okay, that is very important thing. So if any negative value, so or positive value in general, this field is for the arithmetic operations. This field is 16-bit 2's complement format representation of the value. All right. Now coming back to the J-type instruction. So J-type instruction has two fields. One is opcode, which is most significant 6 bits, and an address, associated address with that. So assembly code is mnemonic and address. For example, jump to L2, opcode 8, and then we have some some values corresponding to L2. We'll be discussing that, how from a label number, how we can determine what is the value here need to be put. Okay, what is the value here need to be put. There are some complexity associated with that, but we need to understand more about this addressing and spacing, placing of the instruction in the memory, and so on and so forth. We'll pick up that later in the semester. Okay, but at this point, just imagine you know how to translate L2 into a value. So you represent that value in a binary. So that becomes your machine code and corresponding hex code. So this is what we discussed so far is an assembler. As an assembler, how it generates a machine code for the program. So it's pretty much straightforward. You look for the mnemonic, you know the code, you know the what type it is, then look for the other fields to fill up the bits in those positions.